Hi, I'm Meta Spencer. Today, how about talking about clouds? We haven't had a conversation about clouds in a long time, and that's what we're going to do. We're going to Nevada, where there's an institute called the Desert Research Institute, and they do research on clouds and very important research having to that is extremely important as a possible way of managing climate change. So I have two friends there. One I've known a couple of times before, and one is brand new. Dr. David Mitchell is a researcher at the Desert Research Institute in Nevada, and he knows a thing or two about cirrus clouds. And his colleague, Dr. Ehsan Irfani, is also there at the Desert Research Institute. And he has some clouds behind him, which he says are pretty thunder clouds, and he will show us those. But I think we'll see more about cirrus clouds. I think I'm going to do a little a wild attempt to set this up so people will know what we're all about. Let's say all clouds, as and you guys are going to correct me because I'm going to walk right into making big mistakes. But anyway, let's say, as I understand it, all clouds do two things. They can both have some effect on warming the planet, and they have some effect on cooling the planet. And which predominates in any one case will depend largely on the nature of the clouds and how far up or down they are, how high or low. So the low level clouds, as I understand it, mainly cool the planet. And we do a lot of things. We have various options that can be done to whiten those clouds and to do things that would maybe help cool the planet even more. But the high clouds are wispy looking things called cirrus clouds, and they're up in the very high stratosphere, and they are full of ice. And their predominant effect is to warm the planet, keep us warm. It's like a blanket. And as with a blanket, if you poke holes in the blanket, you can let some of the heat out. And I think these guys have been working on a plan to poke holes in the blanket and let out some of the heat from the planet at the north and south poles, so that would be one way of reducing climate change. Now, guys, David Mitchell, how silly is my beginning?
That all sounded good to me.
Sean, do you have any corrections to make?
No, I think it was a good introduction.
All right, good. Well, so you fellas are working on a game plan that could make a big difference. Wonderful idea. And of course, you're going to find people who are scared to death that you're going to do something that will create a catastrophe on Earth. But I want to know, I want to spend the time this whole hour talking about your research. And so I'm gonna ask David, because I hear you have some slides that you want to show us that explain what I tried to start off with. Okay, go for it, David.
I just called this fundamental advancements in cirrus cloud thinning research, because the research we're doing on cirrus clouds is pretty fundamental. It applies to climate change outside of cirrus cloud thinning. It's relevant to climate models in general, to cloud physics in general, to atmospheric science in general. And the reason for that is shown here. I'll skip that one slide. As stated in the 2023 United Nations Environment Program report, One Atmosphere, an independent expert review of solar modification research and deployment. This was a report that came out from the United Nations Environment Program. It briefly describes cirrus cloud thinning, and I made a little cartoon, or actually this is from a paper by Trudis Storelfmo and co-authors in 2013 that kind of describes what's going on there. But the report basically is saying that the cirrus cloud thinning idea is we don't really know what the feasibility of it is, in part because I put in bold here, larger uncertainties associated with the ice nucleation processes in high clouds. So what that means is that there's two pathways for ice crystals to form in cirrus clouds. You could say two different processes. And one of them involves what they call an ice nuclei, and one of them doesn't. The one that involves an ice nuclei that means a little particle where water vapor condenses on and grows an ice crystal. Usually or very often that's a mineral dust particle, but it could be other things as well. But Mother Nature supplies a lot of little aerosol particles, and a subset of those aerosols are what we call ice nuclei. And that means that water vapor, when it condenses onto that particle, will grow an ice crystal. And the other process called
wait a minute. So,
Yeah.
but the particle itself is not water. The particle is dust or some chemical or some whatever. It's something different from ice and water itself.
Yeah.
And the ice forms around it, on it.
Yeah.
Okay.
It tends to have the dust particle or whatever it is tends to have a crystal lattice structure that's similar to ice. So like attracts like, you could say. So the water molecules line up in a favorable orientation to mimic that crystal lattice that they see, like in a, say, potassium feldspar, mineral dust. And so they orient and deposit onto that crystal lattice, that's an ice nuclei, and start growing spontaneously when this relative humidity is high enough, like more than 100% relative to ice. So that's what ice nucleation is.
Okay, now hold on. When you have dust in the high stratosphere and there's water up there, under certain circumstances, it will form ice lattice crystals on these dust particles, but not necessarily. Is that right? So
Right.
when does it happen and when doesn't it?
What determines whether it forms ice or not?
Yeah.
Yeah, the humidity. So they call it saturation. So when water vapor is supersaturated, you form the crystals. But when it's below water saturation, then the relative humidity is less than 100% with respect to ice, and nothing grows. No crystals are growing.
Okay, now that looks like the left-hand side called unseeded. And what's this thing on the right?
That's when you do have ice nuclei. So when you have ice nuclei, the cirrus clouds tend to be thinner and the crystals are bigger relative to the other process. And the other process is called homogeneous ice nucleation because it does not involve a ice nuclei or a particle. It involves solution droplets. And the solution droplets can be like haze droplets, like less smaller than a cloud droplet, or they can be cloud droplets, but they are containing some salt solution usually. It could be sulfuric acid, it could be sodium chloride, like table salt. It could be anything that's soluble. And the nucleation depends on the activity of water in that solution. It depends on the activity of water. That's a complex topic, and we probably don't want to go there.
No, but I want to make sure I know the difference between these two things, the unseeded and the seeded. Now that there, I'm still not. I'm going to be really tough, requiring you to explain to me as a completely uneducated person, because our viewers are pretty much the same level. So now over here with these unseeded things, they have to have particles of something else. But as I understand it, the things on the right don't need other particles because they can form ice crystals around water or ice crystals themselves. In other words, they don't have another aerosol thing. Is that the difference?
The location is different. It's on the left side is like that you just described. The homogeneous.
Where
Uh,
they
I see.
can, I'm sorry, so the homogeneous ones, they can form ice crystals without any aerosol particles, other kinds of
Yes,
solid. Okay, but the things on the right only form crystals around things that start with a particle, an
yes, like
aerosol.
an ice nuclei particle.
It,
The ones on the left side, the homogeneous side, they also form with a particle, you might say. It would be a solution droplet. It could start as an aerosol particle and turn into, but it's basically got no um, solid particle inside it. It's a solution,
oh,
like sulfuric acid solution or a
okay, now
salt.
wait, this is presumably pretty important. There's a difference between these two kinds of things, right?
Yes, right. Yeah.
So I better understand it. Okay. Now, why is this important?
Because cirrus cloud thinning, or CCT for short, will not work unless there's many homogeneously nucleated cirrus clouds. So the example on the left, you need a considerable percentage of the cirrus clouds forming that way, or the CCT idea is a red herring, basically. It won't work.
Or the CCT idea, meaning cirrus cloud thinning idea will not work.
Correct.
Okay. So you got to have a lot of these on the left before it will work. And then
Correct.
what happens? The things on the right are what's that all about?
Yeah, so those are formed by heterogeneous ice nucleation. And there's a lot of debate in the scientific community on how the cirrus clouds form. Some people argue that most cirrus clouds are formed by heterogeneous ice nucleation, in which case CCT is not a viable climate intervention method. But others say, well, wait, we just don't know yet. And that's what I'm talking about with our new research, is some new advancement in our understanding on that.
Oh, okay. Thank
So,
you. All right. And we should emphasize that CCT is the name of your game. That
yes,
Cirrus cloud thing is what you're going to go down in the history books for having invented, right?
who knows? But I think it's important for science in general to know this. So even without
Okay.
CCT,
All right.
for example, there's a review article by Heimsfield et al. It's called a AMS monograph in 2017. And they listed 7 gaps in our understanding on cirrus clouds. And the nucleation issue that I'm talking about now is number 1 on their list. So that's even without CCT, scientists really feel like this is important knowledge to go forward in
Right.
basic cloud research.
To find out how cirrus clouds are formed.
Yes, yes, the
Okay.
mechanism by
Okay.
which ice is produced. And it's not going to be a toggle switch like one or the other. It's going to be a mixture of both. But our job is to find out what that mixture is. Is it 10% or is it 50%?
Uh-huh.
And where does it
And
change with latitude and
what
all?
do we want it to be? Because I know if you can only do cirrus cloud thinning when you have plenty of these things on the left, when it's largely that, then you're going to want it to be 80% of the clouds are like that, right?
Yeah, for optimal CCT effect, you'd
Mm-hmm.
want that. Yes.
Mm-hmm. All right, onward. Got it.
Okay. So because there's 2 different ice formation pathways, it opens the possibility to intervene in one mechanism, which is the homogeneous nucleation method. You could intervene in that process by adding ice nuclei, because the homogeneous ice nucleated clouds are forming when there's a lack of ice nuclei. They also form when a higher updraft conditions. So it can be either one of those, factors. You could have a lack of ice nuclei in the atmosphere and you're forming through homogeneous nucleation, or you could have a higher updraft, relatively high updraft in the atmosphere, and that will also favor this homogeneous process of nucleation.
Excuse me, but I've got a friend joining us. This is, she will be here in a second. Let's turn off your show screen sharing thing right now so that I can introduce Dr. Adele Buckley, who is a friend of mine and a physicist and a member of the Canadian Pugwash Group. And Adele is, as I say, a physicist, but I've had her and some of the other physics Pugwash members to join me at various times in previous episodes of this series so that I could get some. Adele, show your face. I'm trying to introduce you. So show up and open your come on, Adele.
Oh, wait a minute.
Yeah, show your face. There you go. That's all I want. I'm trying to introduce you and you weren't there.
Hi, everyone. I'm sorry to be late, but I'll follow as best I can.
All right. David Mitchell here is explaining with a PowerPoint the two types of clouds of formation of cirrus clouds. So David, go back to show her your slide and quickly summarize the difference that we've made so far.
Adele, we've been talking about how there's two different methods for cirrus cloud formation, and the reason we care about that is because of these two different ice formation processes, we can cool the planet by intervening in one of the processes by adding natural ice nuclei, or even like silver iodide if we wanted to, which they use in conventional cloud seeding. So the cloud on the left side is formed by a process called homogeneous ice nucleation, where there's no ice nuclei involved, like a mineral dust particle, for example. It forms on solution droplets without any solid particle involved. And when that happens, it produces a high concentration of ice crystals and smaller ice crystals, because they can't grow very fast because they all compete for water vapor. And it's like if you have a limited amount of food in a cafeteria and you have 100 people storming the cafeteria for that food, they're going to have a small amount of food to eat because they are competing for that food. So in a similar way, the ice crystals are competing for water vapor. That's their food. And they all want to eat as much as they can, but because there's so many of them, they can't eat the food that much, the competition effect. So they remain small and thin. In the other example of heterogeneous nucleation, there's only a few people in the cafeteria to eat the food, so they get big and fat. And those crystals are much larger than the other crystals. So they fall faster too on the right side, the heterogeneous ice nucleation. So because they're falling faster, the ice water content in the cloud, the mass of ice in the cloud, is less than it is on the left side, the homogeneous example. So when there's less ice in the cloud, because they're falling it faster, the radiation from the Earth's surface can escape through the cloud. when the cloud's thinner, more radiation escapes to outer space, like thermal radiation. And that's the idea behind cirrus cloud thinning, is you take clouds on the left that are formed by homogeneous ice nucleation, and you add ice nuclei to the atmosphere. And those ice nuclei are going to interrupt the process that's in play already, the homogeneous nucleation process. They intervene in that process by forming at a lower relative humidity than is required for the homogeneous process. And with particles like ice nuclei, they start gobbling up the water vapor at a lower relative humidity, but the homogeneous relative to the other process. So the homogeneous nucleation process requires a very high relative humidity, like 150% approximately, where the ice nuclei, they start growing with water vapor, forming into ice crystals at a much lower relative humidity, maybe 110% or 120%, somewhere in there, even 105% sometimes. So when they do that, the relative humidity drops down. So they prevent the relative humidity from going higher, which is required for homogeneous ice nucleation to happen. So you add a lot of ice nuclei to a cirrus cloud formed by homogeneous nucleation, and that'll depress the relative humidity because those ice nuclei grow at a lower relative humidity than is required for homogeneous nucleation. And those ice nuclei crystals are growing more and more and more. And as they grow more and more, they reduce the relative humidity to the conditions that they form at. So that basically hijacks the whole process for homogeneous nucleation. It can't happen any longer because of those ice nuclei that are keeping the relative humidity lower in the cloud. So it only permits the ice nuclei to grow from water vapor, but prohibits the homogeneous nucleation process that requires a higher relative humidity. So that's the general idea behind the climate intervention method.
Mm-hmm.
And once you have converted all the homogeneous cirrus clouds into heterogeneous cirrus clouds, the crystals are larger in the heterogeneous cirrus clouds, so they fall faster, and their faster fall speeds reduce the ice mass in the cloud. So both the particle size and the lower ice mass content, allow more radiation to penetrate the cloud and escape to outer space. So the thermal radiation from the Earth's surface is going through the cloud to outer space much more readily than it would in the homogeneously nucleated cloud.
Mm-hmm. Okay, so that's the game plan.
Yeah.
You fly up to the stratosphere. That is someplace in the stratosphere, right?
No,
Where?
the clouds are in the upper troposphere.
Upper troposphere, not in the stratosphere. Okay.
Yeah.
There ever any clouds in the stratosphere?
No.
No? And no
Basically
clouds
not.
in the stratosphere. Okay.
There can be in the lower stratosphere, there can be polar stratospheric clouds in the wintertime over Antarctica and stuff, but those are exceptions to the rule, you might say.
I see. Okay, well, that's good to know.
Yeah.
Okay, so now, but you do now, as I understand it, you're going to fly around and you're going to dump little ice cubes, only smaller. Smash up some ice cubes.
Ice
And,
nuclei.
well, ice nuclei, what are they like? How big are they, and how would I recognize one if we met on the street?
You wouldn't recognize it because they're the ones they use in conventional cloud seeding are silver iodide ice nuclei, and they're submicron, like less than a micron in size, like maybe 1/10 of a micron.
Okay, how do you get them that small? Well, that's a different question, but
Yeah, that's a long story. But they have burners that basically burn a fuel that creates an aerosol exhaust of silver iodide aerosol.
Well, this obviously is significant in some way because it helps with the radiation problem, but quantitatively, how much of this do you have to do to even notice the effect? Maybe it's too early in the system to try to figure that out, but if you did a little, would you even notice it was happening, or would you have to do huge amounts of seeding in order to see an effect?
Yeah, to see a radiation effect, that would be difficult because the radiation effects we're talking about are in the order of 1 watt per meter squared, which might roughly correlate to like 1 degree Celsius in temperature, maybe 1.5 degrees, whatever. But it's small effect anyway in terms of radiation and temperature. But if you have a satellite looking at the clouds, the satellite could see a change in the physical structure of the cloud, the physical properties of the cloud, and you could know if it's working because of that. So
how do you measure the amount of heat that's escaping? Is there any way to do that, or you just infer that from other things?
well, if you had a satellite measuring the change in the ice water content of the cloud and the particle sizes in the cloud, you could put that into a model, and the model would tell you how the radiation's changing based on the fundamental radiation transfer theory and that we know about. You put a cloud in, that's what ASON's been working on that.
Now, okay. Now, as I echo Adele's question, would you have to have 1,000 planes flying all the time,
Oh, yeah.
squirting this stuff, or in order to have the effect you want, or would once a year one plane make the difference? How, something in between those? How big a difference will one application of ice crystals make?
Most people I've talked to think that a fleet of drones would be the right approach, where you have several drones, large drones that are they're flying maybe between the North Pole and 65 degrees latitude in either both poles, actually, the northern and southern. And because that's a relatively small area compared to the whole area of the Earth, you wouldn't need a huge number of drones to do that. Maybe just 5 or so. But we haven't really done much research on that. We've been really concerning ourselves with the fundamentals of physics of how the clouds are forming, just to know whether the idea holds water or not.
Yeah. And so far, does everybody agree that it does hold water?
No, not everybody. There's a talk at a conference I went to in Italy last month where the researcher was saying this idea is dead in the water.
Why?
That was based on her modeling work.
Oh.
But the climate models don't know everything. They don't have all the whole process of cirrus cloud formation is complex, as you might have started to understand from this conversation. It involves what they call gravity waves in the atmosphere, and whether the mountain-induced gravity waves are included in the model or not, and it involves other assumptions, how much ice is present at the time of nucleation and things like that. So yeah, I think you got the general idea. So the conundrum, yeah, this is what I was talking about. Almost all climate intervention research has been restricted to climate model simulations that test the intervention methods. But for CCT, the relevant processes are complex and they may not be modeled correctly. So that's what I was just saying. And then so we've taken a different approach here. Instead of trying to make the climate models produce perfect cirrus clouds, which is a tall order in my opinion, we've taken a satellite remote sensing approach and tackled the fundamental issue regarding the uncertainty, which is whether it's homogeneous nucleation or heterogeneous nucleation forming the cloud, or what mixture of the two is happening in nature. So since the fraction of cirrus clouds is strongly affected by homogeneous that fraction of clouds that's strongly affected by what we can just call home for short, that's the main uncertainty regarding the viability of CCT. So let's find out what that fraction is using satellite remote sensing and reduce this uncertainty and then proceed with the modeling after that.
So that's what you've been doing.
Yes.
Okay, tell us about it.
I don't understand what would be satellite remote sensing. What would you be looking for or at?
Yeah, that's a good question. So we developed a new, satellite remote sensing could be anything under the sun almost. It's a lot of different applications. But in this particular application of understanding cirrus clouds, we're interested in the ice water content of the cloud. That's the ice mass content in the cirrus cloud. We want to know how many grams of ice per cubic meter exist. Another variable that we retrieve with satellites is the particle size, the effective particle size in the cirrus cloud. And then, of course, we want to know the number concentration. How many ice crystals per liter do we have in a cloud, in a cirrus cloud? And that'll depend on the mechanism, whether it's heterogeneous or homogeneous nucleation. So if we know those three physical properties of the cloud, we can determine how many, what percentage of the cirrus around the world are being formed through homogeneous nucleation and, on the other hand, heterogeneous nucleation.
And that will tell you how effective you're right there. That's all you need to know to decide what's going to work and whether it won't work.
Correct. So in the past, we haven't been able to retrieve the number concentration of ice crystals. Only since 2018 have we been able to do that. And we've improved our previous technique. So we're getting...
So let's talk about how how you know that this is going to work. What progress have you made to discovering what this lady didn't know? Apparently your friend whoever this colleague in Italy did not know some of the things that you know, and that now you feel you have a different opinion because of that. Can you elaborate on that, or have I got it wrong?
No, that's a good question. So we want to, first of all, we want to know if when we label a cirrus cloud dominated by homogeneous ice nucleation, are we getting it right? How do we know that?
Okay.
We can say that the cirrus cloud has a high concentration of ice crystals, but that tells you that there's a high likelihood that homogeneous ice nucleation is dominating when there's a high number concentration, but it's sort of hard to use that metric alone to discriminate between these two types of cirrus clouds. So we are retrieving these three physical properties of cirrus clouds, so we can use all three of those properties to come up with a better classification, whether the cloud is dominated by homogeneous or heterogeneous nucleation. And we can use fundamental theory, homogeneous ice nucleation theory, to tell us if we're right or not.
Mhm.
And it's very simple theory. It could fit on one page on a PowerPoint slide. I'm not going to go into that, but that's just how simple it is.
Why is it you only want to do this at the poles and in the winter and or when it's winter there?
Yeah.
And why? Why is that specific? I think that it's great that there's a technology that offers some hope that's specific to the problems that occur at the poles, because we know that the poles are, as at least I know the Arctic is melting and getting warmer way faster than the rest of the world. So the catastrophes that are looming are mostly going to hit the Arctic first and make even bigger ramifications from that. So if you've got some technology that's ready to go or anywhere near ready to go that would be specifically useful in the polar regions, that sounds very attractive to me, but I don't really understand why why you're emphasizing this for the poles and not say the equator or where I am,
Yeah.
Toronto.
Because it doesn't work at the equator, and it may not even work in the mid latitudes that well. Because like what your introduction talked about, the clouds have two effects, and one's a cooling effect when they're low clouds, and one's a warming effect when they're high clouds. And that has to do, like when clouds have a cooling effect, they're low clouds, they are reflecting sunlight. That's the cooling. And cirrus clouds also reflect sunlight, but they trap long wave radiation or thermal radiation more efficiently than they reflect sunlight. So they have a bias, you could say, in the warming effect, or a stronger warming effect than a cooling effect. But nonetheless, both effects are there. There's a cooling effect, the cirrus reflecting sunlight, and there's a warming effect by trapping the long wave radiation and re-emitting it back to the surface in the atmosphere itself. So which one of those processes wins out depends on the latitude. And if you go up to the tropics, the cooling effect from the reflection of sunlight kind of counteracts the thermal heat trapping effect. And those two cancel out basically.
Okay.
As the further north you go, the stronger the warming effect is winning over the cooling effect.
Okay, got it. And besides
Yeah.
which, there's not that much sunshine in the winter if that's when you're going to do it at the poles, you wouldn't have that much sunlight coming in to have to be reflected, right?
Right. So what ASON has done is looked at the Arctic night when there's no sunlight at all.
Right.
The only game in town is the long wave radiation or the heat escaping to space. And he's looked into how much cooling effect the CCT would have under those conditions.
All right. And you compared them, Ehsan? You compared the winter and the summer effects at the poles.
We only looked at the impact in the winter, but we use the macrophysical or cloud properties from satellite. We implemented them in the radiative transfer model and calculated the radiation fluxes of long wave or thermal radiation. And that's what we did. We study only for the Arctic night or during the winter. Radiative transfer model is a simple model, but it's helpful to understand the processes. And we looked at two different cloud type, homogeneous and heterogeneous cirrus cloud, and those are based on the satellite retrievals, but we actually use them in the radiative transfer model, and we could see that the pattern of radiation is very different in homogeneous versus heterogeneous. So when we have the homogeneous cloud, it actually has a like the radiation impact in the surface that is it actually has like warmer radiation, or it's like causes heating in the surface, whereas when it is actually heterogeneous cirrus clouds, it actually has a cooling impact on the surface. So a transition from homogeneous to heterogeneous cirrus cloud can cause a cooling impact on the surface. And we calculated when it is
Wait, hold on, let me, because I want to get now, the transition from the one to the other causes a. Now, how is this transition created? Because you're comparing something to something that makes the transition. What, I've lost your,
Yeah.
the argument
Especially-
about what you're doing there.
When I say transition, basically I mean that when we compare homogeneous cloud with heterogeneous cloud, so
Huh?
that's how we saw the difference between these two. That's what we call what we infer as transition. Yeah.
So you know that in the winter, in the Arctic and at the Antarctic, there's a predominance of homogeneous cirrus clouds. And that if you concentrate on seeding those, you're going to have an effect on releasing heat from the atmosphere into outer space and therefore cooling our planet. Is that
That's correct. Yes.
that's it?
That's the
And
general idea, but it's only about 30% of the cirrus clouds in the Arctic are homogeneous dominated cirrus
how
clouds.
much do you need though? And
That's
how
enough.
much difference does it make? If she says, well, that's not enough, you need to have 60% or 80% to make it worth trying. Well, how would you figure whether prove she's right or wrong?
Using a radiation transfer model. That's one way.
Well, if you can knock out even 10% of the cirrus clouds, why shouldn't we celebrate? Go ahead, knock out whatever you can. The more the
Yeah.
better. But if you can't do very much, well, we'll settle for what you can do. Does that make sense what I just argued?
I think so.
It would make sense to go ahead and try. It just, you're wasting a lot of drone time up there doing stuff that doesn't pay off. But if you want to waste your drone time, go ahead. It doesn't hurt anything. Is that it?
Yeah, I think so. But also it's not as bad as that. We're getting about 1 watt. Okay, there's a number of variables at play here. So 30% of the clouds are what you might call home cirrus clouds, or strongly affected by homogeneous ice nucleation. If that's one factor, and then there's low clouds. If there's low clouds around, if they're pervasive, they will neutralize the cooling effect of the CCT.
Mm-hmm.
But it's hard to find information on that though. And what ASON is, we found some hints that there aren't many low clouds during wintertime because it's so cold, it tends to, anything that grows ice is going to take away the low cloud, the liquid water clouds.
Mhm.
So there tends to be, there's some literature anyway that indicates there's probably less low cloud in wintertime in the Arctic.
Mhm.
So, okay, let's assume that we don't have that problem. We have 30% home cirrus clouds. Then you are assuming overcast conditions in this calculation. So if we have overcast skies of pure cirrus, you're getting about 3 watts per square meter of cooling by the CCT effect. And 3 watts per square meter is great. You can cool, that's a lot of cooling potential, but you're probably not having pure overcast cirrus all the time. It maybe 30% is more reasonable. So at 30% cloud coverage, you get 1 watt per square meter of cooling, but that's still pretty good. That's still maybe 1 degree Celsius or 1.5 degrees Celsius, depending on a number of factors.
You mean if you did it all the time at the optimum amount,
Right.
you would be able theoretically to cool the planet by 1 degree or Celsius.
Yeah, to be conservative, 1 degree Celsius.
Well, that sounds good to me if it's not too hard to do. What are the downsides? I've heard people say it doesn't work, or I've read articles insofar as I can read this kind of thing, which isn't very good. But that say, don't bet on this technology as having a future. But I haven't heard anybody say, don't do this because it's going to cause terrible problems for somebody on Earth. And the dangers issue comes up for other kinds of global warming technologies. For example, SAI, people warn about things that might go wrong there. And others. Well, what do they, if anybody is saying, don't have anything to do with David Mitchell because he's going to do some terrible things to the world, what do they accuse you of trying to do?
Some people are worried about the ice nuclei seeding agent. Like, is it toxic? What, like silver iodide is used in conventional cloud seeding. So that the issue that's come up with that is, how toxic is silver iodide? Is it going to poison our plants and animals and that kind of thing? And there's been a lot of litigation about that. And
oh, really? You mean people who've been seeding clouds in order to get rain have been sued for poisoning other people's crops?
No, I haven't really heard that one. But there's a lot of litigation about whether it made it snow too much. So they cause weather problems, like cloud seeding has caused an avalanche, or, too much snow usually is the issue. But anyway, there are going to be those kind of questions, of course. And if you use mineral dust to do the cloud seeding, that shouldn't be an issue, because that's natural. Mother Nature does that all the time. If you use
it would make a difference, because if you sprinkle dirt or anything dark in the Arctic or Antarctic, it's going to discolor the ice so that when the sun comes out, it's not going to have the albedo effect that we need. So I think that is a disadvantage. Excuse me, but I'm your enemy there.
If you did that much seeding, yeah, sure, I agree. But the amount of ice nuclei is just trace amounts. So, for example, with the conventional cloud seeding, they look at the snowpack and they find the maximum level of silver iodide is about 10 parts per trillion. This is really, really low concentrations. You're not going to see that like dust in the snow. So you wouldn't even want to use dust, probably, because the payload on the drones will be too much. Dust weighs a lot. So you'd want to use probably something like silver iodide that's submicron, that you get a lot of bang for your buck, because you atomize 1 gram of silver iodide, that produces a huge amount of ice nuclei that cover a large area of cloud. Because it's 0.1 microns is the mean size of the.
But you never just use tiny particles of water ice, real ice.
Correct. There is a thing called dry ice cloud seeding, where you can use dry ice to freeze everything around it. And that is sort of what you're asking about water. It forms ice crystals because anything coming in proximity to the falling dry ice is super cooled to a very cold temperature. that
Mhm.
forms ice crystals. But that's kind of a different topic.
Uh-huh. So when you get people criticizing you, and you've got to look for it, so if anybody can think of anything to complain about, they will.
Well, I'm a critic.
What is most likely to be a telling criticism? What do you really worry that they may have a point?
Well, I'm not really pro CCT or anti CCT. I would point out that there are concerns about it. And my concern personally is what it would do to the weather patterns. Because when we do this, like ASON's experiment in the Arctic with the radiation transfer model, we found that most of the heating from the cirrus cloud went into the atmosphere. It didn't go to the surface. I mean, the cooling, I'm sorry. The cooling effect of the CCT affected the atmosphere more than the surface of the Earth. And that will it could change the jet stream pattern or something like that.
Mm-hmm.
But it also could change it for the better, because there's a lot of researchers that argue that Arctic warming has been changing the jet stream pattern and
Mm-hmm.
causing more severe weather.
Mm-hmm.
And CCT could reverse that potentially by making it back to normal more. So, but that is an area that should be researched, in my opinion. It could turn out that CCT makes the weather patterns more unpredictable and something worse, more severe weather and problems and things we don't want.
Mm.
But it's also possible that it could make a more favorable jet stream pattern.
Mm-hmm. Well, unfortunately, that's not the kind of thing that you can do a little bit and see what happens.
Yeah.
Because, if you monkey around with the jet stream, you can't necessarily put it back where you got it. Dell Buckley, what's your thought?
Well, this is pretty interesting stuff, and I think understanding the atmosphere is really, really important, because playing around with it needs us to understand it better than we do. But very roughly, how many more years of study at the rate that it's going on with cirrus clouds would be appropriate before you actually try experiments? Um, would it be good to try them now, or wait 10 years, or and if you just do a trial, of course that doesn't solve anything. It just gives you more information that it might work. So give me some idea of the timeline.
Mm.
Yeah. It really depends on how much investment a government would put into the research. I think we might be the only group in the United States that's doing this research, as far as I know anyway.
Wow. Because, it's time for a lot of more research. And are you at the stage where the research agenda? If you had the money and if you had the personnel, the exact kinds of experiments that need to be done now and could be done now. Or are you mostly at the stage of saying, well, depending on what we find out in this next step, we can either go ahead, or we know that a whole different set of questions will emerge? You see what I'm asking? Is it a predictable research agenda, or and that you could outline right now and do a whole bunch of different studies simultaneously that have interlocking effects or implications? Um,
Yeah.
What if you were in charge of if the world gave you plenty of money to do research on whether or not and how to do cirrus cloud thinning to save us, uh, would you know what to do?
Yeah. We've thought a lot about that. And what we need to do, in my opinion, is improve the climate model so that the properties of the cirrus clouds that we see with the satellites, those are at variance from what I've seen with what is going on in the climate models. The climate models aren't producing the cirrus clouds that are seen by the satellites. And the big issue there is the amount of clouds formed by homogeneous ice nucleation. Like I talked to Ulrike Lohmann at that conference last month, and I said, well, Ulrike, it's my understanding that your model simulations of CCT predict that heterogeneous is the dominant mechanism, that it's almost all the cirrus are formed through the heterogeneous process. And she said, yes. And that'll make a big difference, or that is a big difference compared to what the satellite remote sensing is seeing, where we're getting maybe on the order of 20, 30% of the cirrus clouds as home cirrus clouds. And then in addition to that, the home cirrus clouds are optically thicker cirrus clouds, so their radiative impact is much greater than the het cirrus clouds, those produced by heterogeneous nucleation. So when we came up with a proxy for the cloud radiative effect, like how much impact the cloud's having on radiation. And it looks like around 50% of the radiative impact of all cirrus clouds are due to the home cirrus clouds, the homogeneously nucleated cirrus clouds. And that's outside the tropics. So that's mid-latitudes and high latitudes. The home cirrus clouds in the wintertime are controlling over 50% of the radiative effect of all cirrus clouds. So that's a large impact that the home cirrus clouds are having, and the models don't predict that.
Okay, now if you have to decide who's telling the truth, the models or your satellites, I assume that you trust your satellites more because that's an empirical observation as opposed to the predictions or the theoretical results of your assumptions being put together in a model, right?
Right, and we also compare our satellite data with aircraft data, where the aircraft directly go into the clouds and measure the properties, and we get the same result as the aircraft.
Ehsan, are you satisfied with the state of knowledge now that you've been able to generate? Do you feel confident that you're betting your career on this, right? You're betting that your research is going to be the way forward that's worthwhile for you to spend your life doing. How good do you feel about this whole prospect? Do you think you're going out on a limb that's pretty wobbly or thin and liable to crash? Or are you convinced that this is really something that may damn well save the world?
So before I answer this question, I just wanted to add something regarding the importance of climate models compared to observation. And what you said is correct, that observations, we can take them as like the truth, but we also need models, because a climate model can give us like the feedbacks and different mechanisms. For example, if we have a model and we run that with a scenario of like a CCT implemented with that, we can run that for, say, 100 years, 200 years, and then see how the CCT can impact in a long term. And that's important for us to have, because we want to see the long-term impact. But that can be true if the model works through. So we want to have a climate model with correct parameterizations and mechanisms to give us a good answer. So I just wanted to add like why we need models and a good model for CCT or any other climate engineering. And regarding your question about the path of climate engineering, yes, I think that's a good question also, and it's a good concern to have whether any kind of climate engineering works or I saw people, because I'm also involved in MCB, Marine Cloud Brightening, and as you know, there are more researchers in US or all around the world working on MCB. And the timeline that I saw people mentioned in that community is around maybe 10 years to do the required research and testing the climate modeling, also doing the field campaign, and then implementing for like an engineering part. That's the timeline, 10 years. But the thing about research on climate engineering is that it's not just about engineering. It's also about the basic science of the aerosol and cloud interaction. And that can also improve our knowledge regarding the observation and also modeling. So that's the part that I'm like maybe more tend to do the research, is that it's not just about the engineering. So whether it works or not, it's about advancing the science as well.
Oh, it's a lot of fun, I'm sure. But some of us are scared that the world's coming to an end practically. Civilization is going to about collapse. So we are in one hell of a big hurry. And I want to urge you guys to take, you shouldn't have to be told that there are reasons to worry, that you got to hurry it out. And so I'm sorry. Anyway, I should turn to Adele for the final word, because Adele, I honestly, we should keep going to keep this going, but we have to end it up. Adele, what's
Well, what I am hearing is that this research is in some kind of middle stage, or maybe it's infancy. I'm not sure which. And it would be important to involve a lot more researchers, which may or may not be practical. But I think there needs to be more people and funds and projects and whatnot in place to try to flesh out all of the answers that you don't have so far, because you can't apply this yet, and I think you both agree, because of a whole bunch of missing links. So my guess is you need more research and more researchers to keep on going on this.
Sure, no doubt about it. Okay, we've gone 40 minutes over time. So no, 20 minutes over time. So I thank you all of you, and I think I understand a part of what you said. So if I do, I think some of our viewers will too, and that's progress. If we can spread the word about the research that you guys are doing, it's very, 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 very important. So onward. Thank you for doing it, and talk to you another time. Thanks.
Thank you for the opportunity.
Okay, bye. Project Save the World produces these forums. This is episode 595. Watch them or listen to them as audio podcasts on our website, tosavetheworld.ca. People share information there about 6 global issues, and we welcome your comments too. To find a particular talk show, check the scroll list on the homepage or use the search bar. Project Save the World also produces a quarterly online publication, Peace Magazine, which now serves as a free of charge newsletter to help mobilize knowledge about 6 global threats to humankind. We gladly email the magazine as a PDF or link to any interested organization in the world that works to prevent a global catastrophe involving war and weapons, global warming, famine, pandemics, radioactive contamination, or cyber risks. Just email us at office@peacemagazine.org and we'll add your group's email address without charge to our list. Please type "subscribe my group" as the subject of your email. For individual subscriptions at $20 Canadian per year, go to pressreader.com on your browser and search for Peace Magazine.